Now, we've talked about how to simulate random numbers from simple probability distributions, but the question now is, well, what if you want to simulate data from a model? So, for example, like a linear model. So I've got a very simple linear model here. It has a single predictor x, and it's going to have random noise, what I call epsilon, that has a normal distribution with standard deviation 2. The outcome is going to be generated with using these two regression coefficients. I've got an intercept beta naught and a slope beta 1. I'm going to assume that beta naught is equal to 0.5 and beta 1 is equal to 2. So the question is, how do I simulate from this model now that I've specified what it is? So first I set the seed. Remember, it's always very important to set that seed. So I set it to 20. I generate x, the predictor, which has a standard normal distribution. I generate epsilon, which is going to have a standard normal distribution with mean 0 and standard deviation 2. And then I'm going to add them all together after multiplying the regression coefficients to generate my y. And so from the summary here, you can see that y has roughly a mean of 0.68. And it ranges from about -6 to +6. And then I can plot the data to see what they look like. And here they are on the next slide. So this is the plot of the x that I simulated and the y that I simulated from the linear model. And you can see that they very clearly have a linear relationship that follows the model that we specified. So just a slight variation of the previous example. What if x is instead of x being a normal random variable, what if x is a binary random variable? So maybe it represents gender, or maybe some treatment versus control or something like that. So here that's very simple. I can generate binary data using the binomial distribution and the R binom function. So I set the seed again. And I generate 100 binomial random variables, and these are going to have this comes from the binomial distribution, which is n equal to 1 and p equal to half. So the probability of 1 is going to be equal to 0.5. So I generate 100 of those, and then I generate my normal random variables, my normal error term, which is going to be mean 0 and standard deviation 2, and then I add them all together to produce my y. So now when I look at the summary of y, I see the mean is about 1.4, and it ranges from about -3 to 6 or 7. So when I plot the data, of course, they'll look very different, because the x variable is binary, but the y variable is still continuous. It's normal. So here you can see that there appears to be a pretty clear, again, linear trend between going from x equal to 0 and x equal to 1. Now suppose we want to simulate from a slightly more complicated model, a generalized linear model, perhaps with a Poisson distribution. And so, for example, we might want to simulate some outcome data that are count variables instead of continuous variables. So we have to use a slightly more complicated approach to do this, in particular because the error distribution is not going to be normal. It's going to be a Poisson distribution. And so let's assume that the outcome y has a Poisson distribution with mean mu, and that the log of mu follows a linear model with the intercept beta naught and a slope beta 1. So x is going to be one of our predictors. So let's assume that beta naught is 0.5 and beta 1 is 0.3. So how do we simulate from this model to get our Poisson data? So we need to use the R-Poise function for this. And so we first set the seed, as always, and we generate our predictor variable x, which is going to have a standard normal distribution. Then we're going to generate our linear predictor log of mu, which is just adding the slope and the intercept and the slope coefficient times x. So that's the log of our linear predictor, but in order to get the mean for our Poisson random variable, we need to exponentiate that. So we simulate 100 of these Poisson random variables using the R-Poise function, and we give it the exponential of our log mean. So when we summarize this, you'll see that the mean is about 1.5, and it ranges between 0 and 6. When I plot this data, you'll see that they look like Poisson data, and that there's clearly a linear relationship between x and y. As x increases, the count for y generally gets larger, but the data are still count variables here. So the last function I want to talk about is the sample function, and the sample function allows you to draw randomly from a specific set of objects that you specify. So if you give it a vector of numbers, it allows you to draw a random sample from that vector of numbers. And so you can kind of create any arbitrary distribution that you want by specifying a vector of objects and then sampling from it. So here, for example, I'm going to sample from the integers 1 to 10. So I pass it the vector of integers 1 through 10, and I tell it that I want to sample randomly 4 of them without replacement. So, I'm just choosing 4 random entries from 1 to 10, and here I get 3, 4, 5, 7. If I do it again, I'll get 3, 9, 8, 5. So in this example, I won't get repeated numbers because I'm not sampling with replacement. I don't have to just sample numbers. I could sample letters if I wanted to. So here I'm taking the letters A through Z, and I'm just going to sample 5 of them without replacement, and I just get Q, B, E, X, and P. Now, what happens if I don't specify anything? I just give it the vector of objects. So here I'm passing sample the vector 1 through 10. And if I don't specify anything else, what it does is it gives me a permutation of those. So here the vector 1 through 10 is just permuted in a random order. If I call it again, I get yet another permutation. So lastly, if I want to sample from 1 through 10, but with replacement, I can specify the replace equals true argument. So now I'm sampling 1 through 10. I'm getting a vector of 10 numbers from the vector 1 through 10, but because it's with replacement, I can get repeats. So you can see I got 8 3 times, and I got 9 multiple times. So that's how you sample with replacement. So that's a very quick summary of the simulation functions in R. You can draw random samples from specific probability distributions with the R function, so R norm, R pois, R binom we saw already. All the standard distributions are going to be built in that you will need, things like the normal, the Poisson, the binomial, the exponential, gamma, etc. All those functions are built in, and you can use the corresponding R functions to simulate from them. The sample function can be used to draw random samples from arbitrary vectors, so if you want to kind of create your own distribution here. And then it's very important to remember to set the random number generator seed anytime you simulate data in R, so that you can reproduce the results that you've got at a later date.